Another draft physics, draft science here on YouTube video presentation. This one on charge, sort of a draft version of the, more sensible answer to the simple question. And this question is, what is charge? So I don't have all the answers yet, but mostly. Some pieces more than others, and so I'll go through the basics of what it is. What I think is the simpler, better answer to the question. Conventional physics really doesn't answer the question at all. They've invented something called the virtual photon, which doesn't sound very good. Doesn't sound like a physics answer to the question. It just sounds like a placeholder for the real answer. So the simple idea is that wow, that's really not very bright there, is it? You can't see that at all, can you? Well, there's two things, right? You got a proton, and we'll call these electrons. Maybe the pink will work better. Let me just see. No, that works just as crappy. Let's see, do I have any other colors in here? Oh, yellow. We could try that. Well, that's too much like white, so that won't work. Let's see. It's just not drawing very well. Don't like either one of those. Alright, so far so bad. I do have green. This chalk seems to get crappy over time. Ooh, okay, we might go with green. Alright, sorry for the delay. It's always, it's a little work doing this stuff. Anyway, alright, so, the idea is that I put these two things in the same field and they react completely different. So what charge means, it just means basically that something hits these two things and one of them moves this towards it and the other one will move away from it. I'll just use that for the sake of that right now. And so that's it. You hit it with the same thing and they act completely different. So my simple explanation for that difference is 2 plus 2 plus 2 physics. There's two kinds of matter, okay? The proton and the electron, and that's pretty well established. And to go with it, there's two kinds of force. So if an electron force hits a proton, what happens is somewhere in the mechanism, what I'm going to argue is happening, is there's just this exchange where you can sort of understand if two things hit each other, the action is that this one, the white one goes this way and the green one, which you can't see all that well, goes this way. Maybe I should try to see if I can get this pink to work. That might show up better against the green. Just keep fiddling with it. Man, probably better. Probably. Alright, so we'll try that. So the one force goes one way, the other force goes the other way, and nothing gets moved. So if an opposite force hits this object, the proton doesn't move, and all that happens is the force, as you see it anyway, would end up just going that way. And unstated in this, is that some other force is going this way. This force could be going that way. So that sort of explains one reaction. And the other action would be if the same force hits it. So if a pink hits the pink, then it basically creates momentum. That is, it pushes it. So, and it's kind of just that simple. It pushes it until some other force coming from the other direction tells it to stop pushing it, and then it reflects. And that's your equal and opposite reaction kind of thing. So a proton or an electron, and the idea is the protons are less mobile. They're heavier. So they get stuck in the middle of atoms because they're heavier, harder to move, and the electrons end up being the things that are mobile. So the basic idea is, going back to the gravity argument, is that these objects are sitting in a field of mixed energy. The universe itself and its unaffected state would basically have an equal amount of these two forces in them, and everything would be subjected to being hit by the force. So no matter where you'd be in the universe, this stuff is constantly hitting you. And so the idea is that this momentum force, though, can end up, because it does this causing momentum, it does push things in a direction. So if you can have a few of them, they can actually stack up. You know, you can end up with having a few of them hit you, and then your speed goes from, say, 1/10 of the speed of light to 20% of the speed of light to 30% of the speed of light. Depending on how many of them hit you, you go faster and faster. So they pile up behind you. They can, which means that if you run into another opposing force of the same, so say you've collected a few in one direction, just because of circumstances, there's more of these little pink things coming from one side than the other. Kind of like when you're in gravity, because gravity has absorbed some energy, there's less coming out of the earth than is coming down. So as you're falling in gravity, what you're doing is collecting them. And then as you crash into force, that is, as you move faster and faster, you move into more and more force, these would start reflecting off one at a time for every time you get hit. And essentially what the object is going to end up doing, it stops and then it goes, and then it stops and it goes, and it stops and it goes, because they're just making these exchanges. So it's basically a lot of, interactions where the force bits, you could think of them as interacting with each other, but they have to do it through the conduit of the piece of matter. The matter is just a catalyst or a conduit, or it makes it possible for two forces that can't interact in free space to interact. See, if in free space a pink hits a pink, Jesus, this could do better. You could argue that they just bang off of each other and the universe looks exactly the same as it did. You could argue they go right through each other and the universe looks exactly the same as it did. So you can't change the universe when two of the same force hit each other. The only way you can change the universe, that is, have something new happen, is this idea of two opposite forces hit each other, and then you're going to be able to see the change, because if they reflected, the universe is different, because it's now going to have a green thing going that way and a pink thing going that way. And of course, if they do this, that's also a pretty substantial change in the universe. So that's the simple premise, that the forces, whether they interact with each other or they don't interact with each other, doesn't matter, because however they're interacting, the product is, a rational universe that's made out of those actions. In the case of them hitting each other, nothing happens. And in the other case, I would say they don't hit in free space. They need to hit a matter bit the idea would be as the two forces are in different planes of the universe, and this can't happen in free space, where an electron force hits a proton, because they're not dimensionally capable of hitting each other. Second, third dimension kind of thing. And so they need the matter bit to be able to allow this interaction to take place, where the two forces can interact if they hit a piece of matter. Alright, I don't know if I'm terribly in love with this beginning, but we'll live with it. I'm not going to start over. Sorry. Eraser. Yeah, well. Alright, so... Alright. It'll take a second to dry, so that's a problem. Anyway. Alright, so where do I want to go from here? Alright, so now we have a reasoning or a logic to explain why protons and electrons, just with that simple argument that there's two kinds of interactions. And you can sort of understand that if an electron is facing a proton, what's happening between them is any pink force that hits the green object is going to leave okay, in some tangential direction, perpendicular, and also any green force that heads this way is going to end up leaving this way, okay, whoops, without imparting any momentum. So there's neither object is pushed away from each other, because the interaction is really just allowing forces to do it. So I could put in like a dotted line of, you know, what's really happening is that this force went in this way, and this force took an object going this way, okay, and sent it this way. So you could sort of understand that that's the real interaction, that some proton force went that way inside an electron, or an electron force went that way inside of a proton. Anyway, but that part you don't need, I don't think, to get this basic part, so this just confuses things. So the point is it's basically a right turn or an in and out, just kind of depends. The rule would change depending on the circumstance. But you can see that that would create no reflections inside here. These two can't cause anything to reflect because everything's getting diverted. So there'd be low pressure in here, you could understand, because nothing can reflect. And then if I create the opposite circumstance, so put them in opposite positions. The opposite circumstance would be the proton next to a proton, or an electron next to an electron. You could sort of understand that these forces, okay, the force would hit, cause this momentum in this direction, but eventually it's going to hit another force heading this way, another pink bit, and that's going to stop it, right? And this is going to reflect. And then the same thing is going to happen on this other side, and then they're going to have a reflection. So any proton force stuck between two protons is going to end up reflecting kind of endlessly. And the closer they get to each other, you can understand how, well, they're going to reflect more and more and more, because the distance of the reflections are getting shorter and shorter and shorter, which means the pressure pushing on them this way or this way just keeps increasing as they get closer, and decreases as they get further away from each other. So that explains the repulsive force that's absent in gravity. By the way, none of this changes gravity, just because the two actions are completely inverse. So whatever the protons are doing, in gravity, the electrons are doing the opposite, and vice versa. So it doesn't change the fact that gravity itself just uses up the force. So I guess I'll throw that in just for understanding. So basically, when the momentum thing happens, when the same force hits the object and it moves, it's moving less than the speed of light, this thing. So going to its new position, it goes to its new position slower than the speed of light, which means the force essentially lost some momentum. For the period of time it's pushing the piece of matter, the electron or the proton, it's moving some fraction of the speed of light, which means the force itself would have been here in space, and instead, when it finally causes another force to reflect, obviously the opposite force is going to reflect, and so it's like this is going to be replaced by the reflection of an opposite force, and the opposite force is going to be replaced by this reflection. But the point is they're going to be delayed in their progress through space by the fact that they had to move or stop an electron. So pushing an electron or reflecting, if you hit one that's already moving, takes up a little bit of time. The pushing part is the real part. The reflecting doesn't take up any time, but the pushing takes up time. It slows down a piece of force in the universe, and therefore it has less momentum, total momentum. In its travels through space, it won't travel as far. It won't travel as much distance because it had to push an electron or a proton. Alright, so, yeah, that's probably okay. So that explains why there's pressure, low pressure and high pressure, which is just saying why there's attraction and repulsion between electrons and protons and electrons, inversely. All right, so now, if you could theoretically put two charges, keep them close together. Well, I've sort of explained this before, but that's what's sort of happening inside the atom. So you could say that if these were protons, and this was an electron, and that's essentially what, they've already pretty much established that when you put a proton and an electron really close together, you basically have a neutron. And you basically have a hydrogen atom. The hydrogen atom, neutron, same thing, and you're really just talking about the distance between the proton and the electron. The difference between a neutron and a hydrogen atom probably is just as simple as, just making more distance. Okay, this would be a hydrogen atom, and, if they're right next to each other, that would be a neutron, theoretically. Something that simple. But they're constituent. They're elementally the same thing. They have the same pieces in them. So the idea would be inside the nucleus, there's always the strong forces argued to exist, because they say, how do protons get so close to each other? Because they hate each other. How can they be smashed into a nucleus? And the way they're smashed into the nucleus is the fact that just sticking an electron between two protons means all the energy leaks out, and therefore there is no real pressure between them, because nothing can reflect, and so it enables a proton to get really close to an another proton merely by having an electron in between the two objects. So you can smash them very close together. And that's essentially, once you start building your nucleus, then you can have the electrons that are just picking up the extra proton energy that's going to exist in certain spots. So if I'm building an atom, I guess I'll do that really quick, just throw it in. If you're if you're building an atom and you have a net positive in the nucleus because you haven't, the neutrons are neutral because they have both a positive and a negative charge, but the protons, the extra protons and the extra are real extras. Okay, so they're real extras. So you can understand that there's neutron, electron, proton pairs that are proton, electron pairs. Okay, they're in here bonding all this together. But the fact is it has a net positive charge, and the electrons sit out here on the outskirts, and what they're essentially doing is they're repelling each other this way, and they're attracted, going this way because of the absence of force, and there's a tension between those two things, this dislike for each other and their attraction to the nucleus, and so everything's in kind of a tension. So there's lots of, this is the energy of the nuclear bomb. It's essentially this energy that's bouncing between the electrons, and that's what's essentially, once you start releasing all of that energy, it's a lot of energy, because the atoms were made inside of very high pressure. That is a lot of this stuff moving around, a lot of pressure, and so in a sense they have the pressure of the environment they were made in, and they just happen to be durable enough to survive outside of that environment. There's only 100 of them that can do that. There's only 100 arrangements of electrons and protons that can survive in free space. Simple argument. And some of them don't survive very well. Obviously there's a few of them that end up being radioactive in the sense that they just start falling apart when you put them in free space. Take them out of that high pressure. Slowly falling apart, of course. Alright, so so if I could put charges close to each other, an electron and a proton, you could sort of now start to see, we'll just put a positive on this one, put a negative on it, doesn't really matter, pink, red, blah, 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 that they end up having a similarity to what, we consider north-south on magnets. It's essentially the same function. So if I could actually push these two, create the neutron, and let's say the neutron wasn't, spinning, which it must be doing to be neutral, I would argue, to some extent. But whatever, just imagine you can make one of these things. It would behave just like a magnet in the sense that if I put something the same configuration just inverted over here, you could understand that these two are going to have very low pressure, and there'll be low pressure between these two. They'll have high pressure going the diagonals, but that's the longer distance, and so obviously the low pressure is going to win, and the two things will end up moving towards each other because of the stronger lower pressure. So they'll behave just like magnets. So if they were in the same configuration, they're going to try to turn to, match the circumstance. The circumstance is going to cause the repulsion, and that'll cause them to try to fit to the environment. They'll be pushed, they'll be forced to do what magnets do, which is turn and twist and do all kinds of things. All right, now the trick is that magnets, although they have everything in common with charge, the one place their similarity fails is that if I take a regular magnet and I put a charge, an electron out here or a proton out here, I don't get the same reaction. The proton and the electron don't seem to react at all to the magnetism. It's like they can't see it. And I would argue that's because the magnet's more complicated in terms of how it's producing the charge, and that's all. So instead of, it's made of domains, see, it's nice to think that the magnet is just a magnet all the way down, that I could just make a bunch of little magnets, which I have done in the past and trying to explain it, just say it's a bunch of little magnets. But it really isn't. It's a bunch of magnets in a pattern, domains. And the domains are what's really controlling the magnetism. So you could argue, or I could argue, that the reason why magnets can't move charges, and that's the only reason why we don't call magnetism charge, it's the only reason why the north is called the north and the south is called the south instead of calling it positive and negative, is because of this little gap in their relationship. So this little gap between a proton and an electron, the gap is that the magnet is a much larger object made out of atoms, and atoms are creating the polarity. Okay, the shape of the atom is what's causing it, because the atom's got more electrons, a little bit more on one side than the other. The atom's a little bit misshapen. Okay, so its charge isn't even because it's got more electrons on one side than it does the other side. And so now it's polarized. So now it has basically an end that looks greener and an end that looks redder. And so and it's those atoms in arrangement, and those atoms have to arrange in the sense that they have to fit with each other. Once the atoms start becoming polarized, they have to find a comfort with each other, where they're not repulsive. So that's what's causing the changes. And so I would argue that the domains might just be the fact that they might just start at a center and end up creating a magnetism in rings. And if they did do that, if the magnetism was that the atom starts off polarized in the center, and then that polarization dictates the configuration of the next row of atoms, okay, and then the next row is configured by has to match that, so it has to go plus minus plus minus plus minus in terms of how they're turned. And so if you do that, you can understand that the south end is producing exactly the opposite pattern. That is, it starts off pink and then it goes green and then it goes red. And now you have the circumstance where they can mismatch. That is, if I flip them on top of each other, they have to match the pattern. And if they match the pattern and they're the same, well, then they're going to repel. And if they don't match the pattern, it's the opposite pattern, well, then they're going to attract, because now they're opposites. But the key is that an electron and proton can't see the pattern. It just sees, layers of on and off. And from its perspective, it's going to get pushed just as much by the red as it is the blue, in terms of if it moves towards if the pattern's coming out this way, you know, spreading in this kind of shape, you can sort of understand that if a single electron started moving into that, it would hit green, and then it would hit pink, and then it would hit green, and then it would hit pink. If I try to make a straight line, I'll intersect a bunch of these green and pink lines, and so I'd end up being repelled and then attracted, then repelled, then attracted. And I could never get anywhere because I'd just be constantly hitting the wrong force, the wrong piece of the pattern. And as I hit those different pieces of the pattern, I'd just be told, well, 1 minute it tells me to come in, the next minute it's telling me to go out, because I keep intersecting the wrong colored line. So I can just, I don't know how to draw it exactly, because I can't draw it to scale, but it's like they were, you know, in this kind of configuration coming out. So if the electron goes in, it hits a pink, and that tells it can go in, and then it hits the, you know, if it goes in, it hits the green, and that tells it to go out, and then it's right back in the same place where now it's hitting the pink, and it tells it to go in, and then it hits the green, telling it to go out. So it can't make any progress because it keeps hitting the pattern that keeps reversing. So it's just reversing the reversing pattern that explains the distinction between the attracted, creating the low pressure and the high pressure, getting hit by a force that compels you to move away, or a force that's really the absence of a force. So the real argument is that from a proton's perspective, or electron, this is a real force because it's going to cause it to move, and this is a nothing force because it's not going to give it momentum, you know. So then it's just clearly an absence of being affected, and the absence of being affected is going to, I should have done that. Yeah. In the net circumstance is just an absence of pressure. All right. Let's see, what else do I have to add? Yeah, I don't think there's, well, I'll take maybe I'll just pause, and then I'll see if I have something else that I need to say. It gets into a lot of, I mean, I want to get to linear accelerators and how, you know, they go from measuring, well, I might as well throw it in there. So the idea would be is that when you end up having some energy behind, you know, the idea is the collection argument. So I've sort of been over this, but if you had if you were in a field of this kind of energy and you moved quickly in it, you'd end up collecting energy in the direction you're moving. So if I can get a proton to start, or let's use electrons just because they're the ones that do most of the moving. So we'll say this is an electron, and it's collected some force in one direction because it got hit by, say, a gamma ray, or let's just call it well, anyway, some sort of photon, because it's compressed energy, and that hits it. And so now it's got, you know, this is 10% of the speed of light, now it's 20%, now it's 30%, and 40%, let's say. So it's going faster because it has more of these bits pushing in this direction. And so now it's interacting with the field, all right? And as it interacts with the field, as it moves into it, the field is going to reflect, okay? And it's going to start killing these one by one. These are going to reflect, and it's going to slow down. But the idea is that you could maintain its speed by just replacing more force, you know, more of this stuff going this way. So in a sense, that's what accelerators are doing, is they're just keep trying to pile up stuff behind the electron in terms of the photonic energy behind it to get it to go faster and faster. Now the trick is that if you make an electron go faster, I would argue that that's kind of voltage. Voltage is the speed at which how much energy you have behind an electron is basically the voltage. And so if you're if you're moving an electron through a wire, or you know, yeah, it's pretty much in the wire. Let's see, that's where it gets a little tricky. Because again, we're back to crystals and domains, and so the argument is the only time an electron is actually being moved is when there's a transition, okay, from like one conductor to another conductor, or one wire to another wire, unless you solder it and create a connection, so then it doesn't have to give up an electron. But the idea is whenever you're making the transition, so if I have two things in space, okay, and I have voltage on one of these, or charge, okay, extra electrons, it's really, the voltage is going to be, in a sense, just pushing how much energy you have behind an electron. So I can have a bunch of electrons, okay, with just a couple of bits of energy behind them, or I can have an electron with a bunch of it. So this would be low voltage, this would be high voltage electrons. And the real thing is that when they're traveling through the conductor, what's really moving is the force in terms of pressure. So if I had, let's say, say these are electrons in an atoms, okay, so these each one of these is connected to its own atom. And the idea is, as I stated, they have these reflections going back and forth, which essentially equals pressure. So all I have to do is push one electron into this electron, and I increase the pressure here. Well, when I increase the pressure, that's going to cause this electron to tend to move that way, which increases the pressure between these electrons, and that electron will move. So this electron moves, creates more pressure here, that causes this electron to move and this electron to move, and they're not really, okay, the electrons aren't really going anywhere, they're just pushing the pressure. And then if I have alternating current, obviously they're pushing them back the other way, and then they push them, and then they push them. So the electrons aren't really going anywhere, and all you're really moving is the pressure between the electrons. So you can argue that you can have this high voltage here where you have a whole bunch of energy, okay, trying to go in a direction. And the key thing is it needs a conductor to keep going. It needs some pressure to push, because the force itself doesn't seem to be able to get loose. Okay, so the electrons are still bound to the atom enough where the electron can't just fly off. So it's still stuck to the atom. It's attracted the last electron. So these are the last electrons in the conductor. So these pressure has pushed electrons, and it's pushed this last one out, but it's not enough pressure to free it. Okay, so the voltage is high, but it's not high enough to be able to push the electron away from the atom. And what it needs is a conductor. So if it has a conductor, then it can push into the conductor atom, okay, and just convey the pressure. You can get rid of the pressure just by moving into that other atom. That atom will push back, and they'll share their pressure, and essentially it can get rid of all of this energy behind it, right? I mean, it's got a bunch of energy behind it. If it can push on another electron, that electron is pushing energy into it and reflecting it. And as it reflects it, we're getting rid of all of this stuff. So it can transfer its pressure. But the trick is it can't fly through empty space, except it can, right? So they say, that a vacuum is a good insulator, but in a sense it's not, because that's the very environment in which we make, cathode ray tubes. So we're clearly shooting the electrons through the cathode ray tube, but we can't shoot them, technically it's an insulator. But that's the difference between the two, right? So in an atmosphere, okay, the electrons don't move freely until you get to a high enough voltage and just basically rip them, force them. But again, you have to have the conductor. You have to have the atmospheric atoms. So the atmospheric atoms are creating a new conductor, essentially. So they end up lining up, they end up feeling that some of the pressure, and they line up with that pressure. And then eventually there's enough of a conductor where this electron doesn't have to jump the gap. all it has to do is push on this electron, that electron pushes on this one, and this one pushes on that one, and then, you know, the ions of the atoms, and then it's allowed to travel. All the pressure can travel through that weak conductor. And it's a weak conductor. It's a very thin conductor. It's a little tiny wire, and that's why it'll often just glow. You know, it'll start tearing the atoms to pieces because it's such a small conductor. And so it'll lose some of its energy by creating a bunch of visible photons or a spark. Okay. So the electron doesn't really travel. Okay. What's traveling is the pressure. And so this electron is, let's see, I mean, I'm trying to think of the right way to say it. Well, I won't bother. Yeah, I won't bother trying to get there yet. All right, I probably should draw this bigger, so I'll do that. All right, so then we have the opposite, well, the different circumstance of the electron on a surface. See, what I'm trying to get to, too, is that, you know, a linear accelerator, at first, it's measuring how much charge ends up hitting a plate, you know, counting the actual electrons. And then once it starts increasing the energy, what it calls the energy, all of a sudden it starts just measuring heat. Because what I'm sort of arguing is, as you increase the voltage, you're not increasing the number of electrons. You're just increasing their speed. So you can't increase the charge. Once you get to a certain voltage, you're not increasing the charge at all. You know, so you'll have the same number of electrons landing. It's just that the electrons hitting are going to be hitting at a higher speed. But you won't be making more electrons. How fast the electron hits the plate isn't going to charge it anymore. You know, it gets charged by you adding electrons. It doesn't matter how fast the electron was going when you added it. So that's the catch. But anyway, yeah, this starts to get kind of complicated. All right, so, well, we probably should draw that in a different color. Assuming a charge. So let's say now I have a vacuum. So I can't make a conductor, so the electron is going to actually have to make the jump. And in theory, by itself, it's not able to. So I can build up quite a lot. I can build up a very high voltage, you know, millions of volts. I can have, you know, literally millions of volts on this, and the electrons just won't go. You know, so I have to do something to make them go, and what they do is they just heat the surface. So they, you know, having the charge by itself doesn't get the electrons free. So they're still strongly enough bound to their atoms. They don't want to break from their atom, but they do have a ton of voltage behind them. That is, each one is being pushed by a lot of stuff, but there's still enough back pressure from the attraction to the proton to just do an even exchange, you know, where they're not losing any energy and they're not gaining any motion. So they're just stuck in a kind of a purgatory of having be under very high pressure, but not enough pressure to break the bond to in the atom. They can't jump out of their energy level, whatever you want to call it. And so by heating it, you know, by shoving another kind of electricity in or something else to cause this wire to start melting, essentially, then you've done enough damage to the atoms where now these electrons are able to jump. They're able to fly across, pushed by all that extra little energy behind them. So the idea is that they're going to lose energy as they travel, because as they travel they're still going to be hitting force that's in the field. Whether they like it or not, you haven't eliminated all the force in the field. So they're still going to be plowing into force, and they're still going to be reflecting some of this energy. So they're going to start losing velocity. It should be back. Probably. So technical difficulties. Anyway, so by the time they hit the plate, they're going to be going slower. So that's why accelerators have to keep accelerating, is because there's always stuff it's going to hit into, and so it's going to start losing energy as it moves. As it moves, it's moving into more energy. So again, it's this hand example. theoretically, if I could move my hand the speed of light, you could sort of understand that every photon between me from this position to this position, every single photon that would have reflected to you, I'm going to be catching essentially. And it's going to be reflecting off my hand, but it's not going to be progressing any faster than I'm progressing. So it's going to sit there right on the surface of my hand. And if I stop my hand here, every photon is going to be in the same piece of space, and you're going to get hit with a ton of little bits of energy that I've collected. So I can collect it in front of me if I'm going fast enough, and obviously from behind me. If a bunch of this energy hits me from behind, then it's going to push me, and I can't get rid of it until I hit an opposite force. So if I have a gamma ray behind me, behind my hand pushing it, I can only get rid of it at the rate at which I hit stuff moving forward. So if there's not much stuff moving forward, then I'm not going to be able to get rid of that energy. But if there's a normal amount, I will go a certain distance and then I'll run out of gas. And so that's why I have to keep pumping energy into, behind the electron, to keep pushing it, to get it go faster and faster, because it has to plow into a field of energy, some energy. It's not a lot of energy sometimes, but it's energy nonetheless. Because in theory, when you get enough charge differential, you're reducing the amount of the opposite charge, because the whole idea is you're deflecting it. So there isn't as much of it in your way between two charged plates. Yeah. So let's see, what else? There's probably more to this story I want to tell, but I'm just not thinking of what it would be at the moment. Alright, so just a quick review. Alright, so, so in space, it's really not a review. So the idea is the electrons and the protons. I could, like I said, they're just matter bits, and so you just understand the charge part, then you can understand the basic function is this: if something's moving, it's moving because force is pushing it. All right, and if it moves, what it's going to do is if it goes from this A to this B, you can just understand that any force that's here or here or here or here that it's encountering, as it moves, it's basically going to reflect all of that because it has energy pushing it. And that's going to reflect, and what you're going to basically do is convert that into reflections that are all going to be much closer and much tighter space. Okay, so you've converted this into this. And the opposite is happening on the other side of you, where you're basically you're taking stuff that was very tight, and now you're going to be reflecting it into much more space. So you're taking stuff that was compressed and you're expanding it, and on this side you're taking stuff that was expanded and you're compressing it. And that's essentially what photons are. Photons are clumps of compression at a distance. So a certain frequency between the clumps is the photon. And so the less distance between compressions, you get you just go up the scale, the electromagnetic scale, and gamma rays would be just very close blobs of energy, clumps. Yeah, I think that's the way to say it. Clumps. And so everything's just exchanging. By moving, you're expanding one part of the universe and you're compressing the other side. And that's all everything's doing, is compressing and expanding when everything's moving inside of atoms, and all this stuff is moving, and then those compressions have a net effect on the atmosphere around the atom, and then the atoms together, they create another field of compressions and expansions. And then us as individuals do the same thing in the environment by pushing other atoms. We're, causing them to all move in one direction, and they're going to cause an effect, you know, on the other side of them, and so everything's just being manipulated. But the origin of all the movement is just the fact that electrons and protons are affected by these forces in this inverse manner, and it's all of that that creates everything else. Just a lot of it. Yeah, so that's probably enough. So, as stated, draft. That's the basis for what the simulations are still being worked on. It's just that the people doing them have real lives, and life has gotten tough. The whole breaking of all economic rationality, and so but it's the pieces are there, and it's just putting them together, and eventually that'll take place, because it's the simple explanation. It's an accountable explanation. Again, unlike conventional physics that just pretends it can create a little piece of math and have fourth dimensions and create virtual transmitters of energy and virtual communications and virtual everything. This is real, and again, mechanical. You can understand, you can follow the little round thing. Whether you're following the force or following the matter, you can follow it. You can see why it happens. Not just assume it happens or just make up a magical solution. All right. So, till the next time and such, so forth and whatnot. All right. So this has been a Draft Science video presentation and such. Close enough.